Okay. Good morning, everyone. We're gonna get rolling fast. Happy Monday. Okay. So we are picking up where we left off. We were thinking about our different factors affecting ventilation. We had gone through lung volumes, lung capacities, and tests that we would do to test for obstructive versus restrictive pulmonary diseases affecting our resistance of the airways versus affecting compliance of the lungs. And we had stopped off with a brief teaser about the difference between minute ventilation and alveolar ventilation. Okay. So this is going to come into play as we move into our diffusion of gases and understanding the oxygen cascade, and ultimately understanding how we effectively oxygenate tissue. Okay. So minute ventilation, super simple. It's just how much air did you breathe per minute. So to do that, you're going to multiply your breath. So your resting easy breath is your tidal volume. So that's our volume right there. Times RR is your respiration rate. So just how many times did you breathe in and out that minute? Now, when we get to alveolar ventilation, which is going to be what ultimately affects how oxygenated your blood is, we need to take into account that the respiratory zone is not your whole pulmonary system, okay? So we know that we have a conducting zone, we have our airways that are not actively exchanging gases. So we had our trachea, we had our bronchi, we had several splits into bronchioles where we don't have gas exchange happening. So we know that that conducting zone is about 150 milliliters large. So that means we've got dead space where that gas stuck in this space is not going to be moving in and out of your blood because it doesn't have this dense capillary network to it, and it doesn't have these nice thin walls that allow for gas exchange. Okay. So when we're thinking about why this matters conceptually, before we take a look at the equation's pretty easy. We're thinking about this space between the conducting zone and the respiratory zone, which in this image is really just your alveolus. Okay, so we're starting out. You've got at the sort of pauses between your breath, right? You've got some air where you have already traded the gases you're going to trade. You've already put the carbon dioxide coming out of the blood into this air. You've already used up the oxygen in this air. So that's what we're thinking of as like our old air, right? So we're not collapsing our lungs every time we breathe out. So that old air is staying in the lungs, keeping those airways open. Okay. And when you breathe in, when you inspire, you're pulling new, fresh air into the lungs. We know that's happening because we are creating a negative pressure, a lower pressure relative to our atmosphere, pulling air down its gradient from a higher pressure in the room to a lower alveolar pressure in the lungs. So this pulls air in, but that new air doesn't get to skip over what's already held in the airways. So you can think of the air that you're breathing as like a column kind of shifting up and down. So you can see that this old air that we had sitting here between breaths, right? This is now moved deep into the alveolus along with some of this fresh air, right? So we've moved fresh air into the lungs, but not everything in that alveolus and that respiratory zone right now is new, fresh, fully oxygenated air. Okay. But we got air in the alveolus. Gas exchange happens. So we've got that thin barrier between our alveolar air and the blood in the capillaries. We know it's really just type 1 alveolar cells making up that lining of the alveolus. We got a thin little basement membrane. Then we got the endothelial cells on the capillary side. That's it. That's all we're crossing. Nonpolar gases can do this easily. They're small enough that they can just kind of squeeze through our cell membranes. So we're good at this point. Okay. So our exchange with the blood is happening as we have this air in the alveoli. We are pulling oxygen out of that air, moving it into the blood, and we are taking extra carbon dioxide that's swimming around in our bloodstream, and we're putting it into that air. So for this next image, we're not imagining anything moving yet, we're just showing with this color change what has happened to, let's say, the concentrations of gases in that air, right? So we've turned some of these blue blocks red because they're now full of carbon dioxide. We removed the oxygen for the portion of that air that was in the alveolus, that was in that respiratory zone. Then you breathe out. When you breathe out, we're pushing that column of air up. So we're removing it mostly from the alveoli, not so much that we collapse an alveolus, but we're moving the air up into the conducting zone, back towards your mouth. That old air is kind of shifting up before we take this fresh air, pull it back down the column and breathe again. Okay. So the difference between minute ventilation and alveolar ventilation, that for minute ventilation, you would just be counting how much air came in per minute. For alveolar ventilation, we're going to say, hey, wait a second. We don't care about this part that was just old air coming back into the lung, right? That's not important for us from a gas exchange perspective. So we're going to delete that out. So that's how we get to this equation for alveolar ventilation. Okay. So we're this volume of new, fresh air reaching these gas exchange areas every minute. So we can see our friend, the minute ventilation is within this equation. All right, so our tidal volume, just that resting breath, 500 milliliters, times our respiration rate was the minute ventilation. But now we're removing our dead space volume, so the amount of air that would have been like still in the conducting zone. And we're doing this for every breath, so also times the respiration rate. So I'm going to ask you a simple version of this to get the idea of how these amounts are going to be different. So our normal tidal volume, we're not changing. We're going to make that 500 milliliters. We're going to say for nice, easy math in your head that your respiratory rate is about 10 breaths per minute. That's a reasonable number for breaths per minute. We're going to have our dead space volume, what we've mentioned here and in our textbook before, 150 milliliters. So let's calculate out what the minute ventilation is and then what that alveolar ventilation would be. Okay, like we got some answers in, so let's take a look and I'll walk you through it. Okay, cool. So more than half of you got this right from those of you who answered. Where's my tool? Oh, are we not sharing on Zoom? It's not great. Okay, cool. So we'll put that back up. Okay. So from our answer choices, even without doing the math, you actually can kind of tell the correct answer here, right? Because we know that for alveolar ventilation, right, we already know that we're taking minute ventilation and subtracting something away, specifically subtracting away our dead space. So minute ventilation is always going to have to be higher than alveolar ventilation because it's a higher number that we're subtracting away from. So for all these round choices, you can see that we had a lower number for minute ventilation and a higher one for alveolar. So even without understanding the calculation in this multiple choice version, you could have gotten to this answer. Okay, but we'll walk through how you get to the precise right answer right now. We'll do it kind of two ways. Okay, so for our minute ventilation, we start with our minute ventilation calculation. So we're multiplying our tidal volume times our respiration rate. So our tidal volume was 500. Our respiration rate was 10. So 500 times 10, 5,000, giving us 5 liters. Okay, so it's as simple as that. That's why we used 10 as our respiration rate here. Make it nice and easy to do in your head. So 500 times 10, and then we just converted from milliliters to liters. So for our alveolar ventilation, we can use this whole equation if we want. So we're going to start with that 5 liters we've already calculated as the minute ventilation here. Then we're going to subtract away our dead space volume, which we have as 150 milliliters, times our respiration rate, again, just still 10. Okay. So if you do it this way, you're taking that 5 liters, and then you're multiplying across here to figure out what's our total dead space volume per minute that we're thinking about. So that would be that 150 milliliters times 10, giving you 1.5 liters. Oops, I think I have an extra 0 there. Okay. But you might also notice that to get to the correct choice of 3.5 liters for that alveolar ventilation, we are multiplying times the respiration rate twice. So we could also have reshaped this if we wanted to go directly to alveolar ventilation and done our tidal volume minus our dead space volume, and then multiply that all by your respiration rate. That would have worked too, right? In which case we would have had 500 minus 150, which is 350 times 10. Okay. So 2 ways you can get there. We're always going to have a lower alveolar ventilation than minute ventilation because we're trying to figure out how to ignore that dead air. That's the whole big point of this. Okay. So now we're going to think about what's going on with that fresh air, what's going on with our exchange of gases. Okay. So here's our overview. All right, so we're going to see as we're moving through our circulatory system, as we're moving through the cardiovascular system, we are moving past the lungs. We are moving oxygen from the air in the alveoli into the blood. We're also going to see that we're moving oxygen from the blood into tissue that needs that oxygen. And on the opposite side with carbon dioxide, right? When we're passing the lungs, we are getting rid of excess carbon dioxide. When we're passing tissue, we made that carbon dioxide in the tissue, we put it into the blood. So we're focusing really on 2 ends here as we're thinking about changes to the amount of oxygen and carbon dioxide in your bloodstream. And ideally, under normal conditions, this should be happening at the same rate at both ends, right? So at your lungs, you want to be pulling in enough oxygen to feed your tissue. And in terms of carbon dioxide, all that carbon dioxide you're producing at your tissue, you want to breathe all of that extra carbon dioxide out from your lungs with all your breaths. All right. So looking at this figure, you'll notice that we have rates for the movement of oxygen and carbon dioxide that allow us to keep the oxygenation and carbon dioxidification, made that word up, the same. Keep the levels of oxygen and carbon dioxide the same in your arteries all the time. We'll have a different value in our veins, but the same in the veins all the time, not shifting minute per minute, right? So you can see down here, we are using up 250 milliliters per minute of oxygen, which means that when we get to the lungs, we want to pull in 250 milliliters per minute of oxygen, and the other way around, right? At the tissue, We're producing 200 milliliters per minute of carbon dioxide, which means we want to get rid of 200 milliliters per minute of carbon dioxide. So we have the same rate happening in the pulmonary capillaries as in the systemic capillaries because we're keeping these levels constant. And we'll actually see eventually that we are going to be changing blood flow too, so that we can keep these rates constant, keep everything moving well. So we could calculate our respiratory quotient. Your respiratory quotient would just be the ratio of carbon dioxide produced divided by your oxygen consumed. That would just give you a number that gives you an idea of how your body is using these gases and producing these gases. We're going to move on to the diffusion of gases quickly before we come back to understanding what's happening in the circulatory system. Okay. So our gases have to move across membranes, right? They're in the alveoli, they have to get to the blood. And on the other end, they're in the blood, they have to get to the tissue. Okay. So one thing that matters is that barrier that they have to cross should be nice and thin for us under normal conditions. We now know that there can be buildup of mucus, there can be changes in pathology that might change this, but we know usually easy to cross. Okay. What's going to matter now that we're thinking about breathing and we're thinking about this idea of fresh air, this idea of old air, we're also going to need to think about how much oxygen is actually in that alveolus, right? And we're going to measure that by the partial pressure of the gas. Same thing for carbon dioxide. We'll have a partial pressure for carbon dioxide. And we're also going to be thinking about how easily does that gas move in and out of the blood? Because different gases like basically mix better with liquids. And we'll see how that plays a role in a second. So that's what the solubility of the gas in liquid means for us, right? So how much gas do we have? And then how easily can we mix it into our bloodstream? Okay. So we mentioned the ideal gas law before when we were talking about relationships between pressure and volume, right? So here it is back again. So our pressure times our volume is equal to nRT, saying that that pressure of the gas overall is dependent on the temperature of the gas. We got constant in there. It's going to be dependent on N, the amount of gas in terms of like number of gas molecules. We got our pressure and volume familiar in here as well. Okay. So we're going to start breaking down those pressures when we say partial pressures of gases. We're going to be thinking about that number of gas molecules piece. We're going to be thinking about how much is our total pressure of like a mixed gas, the responsibility of the oxygen, how much of it is due to the amount of nitrogen that we have, how much of it is due to carbon dioxide. Because our gas mixtures that we're breathing in are not usually pure oxygen, right? Like unless you have an oxygen tank and you're expressly on purpose raising O2 levels, we're going to be breathing in a bunch of different stuff. Okay. So the pressure in the atmosphere is not due to just oxygen swimming around in the room. It's also due to nitrogen, a tiny bit of carbon dioxide, et cetera, right? If you didn't have one of those gases, right, you'd be removing something, you'd be removing atoms, that pressure would go down, right? All of the gases are kind of creating this pressure. Okay. Now, we can just add up the pressure of each gas to get our total pressure. It's just simple addition, right? If you knew the pressure of the oxygen in the room, you knew the pressure of the nitrogen in the room, you just add them together. That would be the total pressure of the oxygen and the nitrogen, which you'll see on the next slide is most of what's in the air. Yep. So when we talk about partial pressures, we are talking about those like partial amounts, the part that's specifically due to an individual gas. Okay. Now that calculation, pretty simple too. So our partial pressure of the gas, which you'll notice in the notation here, right? It's P for pressure, and then we'd specify a specific gas down here. So you'll see like PO2 is going to be a partial pressure of oxygen. Okay. And for right now, these are not the real numbers. You'll see the real numbers in a second. But to get that partial pressure, we're just doing a percentage, right? So if our total pressure was 100 and oxygen was 50% of it, so like 0.5, right? Our partial pressure of oxygen in this gas would just be 50. Okay. That's it. So just the percentage of the total pressure gives you your partial pressure. Here's what the real world looks like. Okay. So for normal air surrounding us, about 79% of it is nitrogen, about 21% of it is oxygen. Okay. So most of it is actually not one of the gases that we're following. Okay. We also have trace amounts of carbon dioxide. That'll be playing a role as we're thinking about our tissue and our lungs. There's some helium, there's some argon, there's other stuff mixed in, but relatively negligible amounts. Okay. Depending on the environment, water can be a factor. And we're going to think about that as we think about what shifts do we see from the air around you as you move into the lungs. Because we might remember that as we're passing through the conducting zone, so passing through your throat, passing through all those splits of the bronchi and bronchioles, one of the things that we're doing is we're warming and humidifying the air, making it nice and friendly for our lungs. Okay. So we're going to start out with partial pressures in the environment around us, but this is not going to be the same thing as partial pressures exactly in an alveolus, because we see changes to these concentrations of gases, specifically because of water vapor as we pull stuff into the lungs. Okay. But for the normal air around us, we wanted to know our partial pressures of nitrogen and oxygen. We would just be multiplying those percentages times our typical pressure in the atmosphere, which is 760. So this is why I gave you some fake numbers. As we were looking at that slide previously, this one you might probably need a calculator for, right? But we've just got, for our partial pressure of nitrogen, if we want to know, we got 79% nitrogen, so we turn this into a fraction. Our typical atmospheric pressure is 760 millimeters of mercury. Right, this time we're not going to make that a relative pressure because we're not comparing pressures, right? So we're going to leave it at 760. So we multiply across, getting a partial pressure of nitrogen in the atmosphere of about 600. And we do the same thing for oxygen. Right, so we're just taking our percentage, converted it to a decimal to make it easy, multiplying times our total pressure in the atmosphere around us, giving us a partial pressure of oxygen, probably in this room, of about 160 millimeters of mercury. So that's how much of the total pressure is due to oxygen. Now, notice carbon dioxide was not a major component here, but carbon dioxide is going to be a major component when we think about alveoli, when we think about the lungs, when we think about gas exchange. So that's another thing that's going to shift as we move our focus to the alveoli. So at 100% humidity, when we have filled up our air, gotten it as moist as we can, still a gas, still water vapor, 100%. Okay, but as much as you can stuff into this warmed air, the partial pressure of water vapor, so that's what that pH2O is, it's about 47 millimeters of mercury. All right. So now, if we don't change that pressure, our overall pressure of the gas that we're thinking about, right? We're leaving it at 760, right? This means that the pressures of the other gases have to shift, right? Because now 47 millimeters of mercury of that is due to our water, right? So we've shifted what our partial pressure of the other gases would be, because this is just additive. So the total pressure is all the partial pressures added together, no matter how many of them there are. Okay. So once we humidify the air, make it really full of water vapor, make it really moist, make it really humid, we've dropped down our partial pressure of nitrogen and oxygen here. So you can see that before, our partial pressure of nitrogen was at 600. Now it's dropped to 563. Partial pressure of oxygen before was at 160. And we're down to about 150. okay? And as we are moving into the lungs, we're going to be thinking about carbon dioxide soon. So I'm going to point out just that we have this really wimpy little partial pressure of carbon dioxide as we've humidified this air, still only 0.21 millimeters of mercury at this point. Okay. So this is the situation. As we're breathing in these gases, they're exerting pressure as gases in your lungs, as they're moving into your lungs. But we're also going to be thinking about partial pressures of these gases in your blood. Okay. So I want you to imagine, like, if you've ever seen or used a soda stream, or if you want to think of like a can of soda or a can of seltzer, right? You can have gases stored in liquid. You know this, right? If you open a can of soda, suddenly all those bubbles are rising to the top, right? As that gas is suddenly trying to make its way into the atmosphere. But if you were to look inside of a fully closed, fully sealed can of soda, there aren't a ton of little jittery gas bubbles moving everywhere at that point. That's because the gas at that point is dissolved in that liquid. It's not until we have pressure changes, not until we get exposed to the atmospheric air, that we start to see that gas rapidly trying to move. Okay. So both are vaporized gases, the ones in the air exert partial pressures, but they also exert partial pressures in liquid. Okay. Now, how much of that gas goes into solution, how much of it goes into the liquid, is going to depend on the partial pressure of the gas in like the air surrounding, right? But it's also going to depend on how soluble that gas is in liquid, right? So if you have a really high pressure of oxygen in the air and you're right next to the blood, that can make a lot of oxygen go into the blood. But if you make a gas or pick a gas that's really soluble in liquid that moves easily into liquid, you don't need actually that much gas in the air to end up with sufficient gas in the liquid. Okay. Do you want to keep in mind, since we are going to be thinking about gas exchange between the alveoli and the blood, right? You want to think immediately our air in the alveoli, capillaries are going to be running next to them. We're going to reach equilibrium, right? So we're going to have gases diffusing in and out. We're going to be able to measure partial pressures, right? But things are going to move in and out until they come to equilibrium. So whatever our partial pressure of oxygen is in the alveolar air, we're going to eventually reach equilibrium with the partial pressure in the blood. However, we need to shift it. And same thing for our carbon dioxide. Okay. So how much of the gas goes into the blood, or comes out of the blood, but goes into the blood is what we're thinking about now, is dependent on solubility. And we can measure this using something called Henry's law. So Henry's law is this C equals Kp here. So what this says is that our molar concentration of the dissolved gas, so that's C, right? So we're thinking of this as vaguely the amount of the gas that's dissolved in our liquid is going to be equivalent to a constant. So you'll like have a constant for oxygen, you'd have a constant for carbon dioxide, times the partial pressure of that gas in the atmosphere. I'm not going to make you do these calculations, but conceptually, this is what's happening. And this is why we care about solubility. So the solubility would be contained like in that constant there. And oxygen and carbon dioxide are not equally soluble in liquid, which is good because we've seen that their partial pressures are nowhere near equal when we're looking at the atmosphere, right? We barely have any partial pressure of carbon dioxide in the atmosphere. So if we want to think about significant amounts of carbon dioxide in the blood and the movement of carbon dioxide, in order to have a number that like matters to us, it would have to be the case that that carbon dioxide is more soluble, which we can see that it is, right? So oxygen has a kind of tough time getting into the water, right? So for the same partial pressure, right? So we're going to pretend we forced the same amount of oxygen into some little container, some beaker, whatever. Same amount oxygen, same amount carbon dioxide, each of them starting at a partial pressure of 100. You'd only have about 0.15 millimoles of oxygen going into the water, but you'd have 3 millimoles of carbon dioxide going into that water if we started at the same pressure. So carbon dioxide, way easier to get into liquid than oxygen. Okay. So here you see that process of oxygen reaching equilibrium. So our bluish purple dots here are our oxygen molecules. You can see our setup starting with a partial pressure of oxygen in the air here at 100. This is a time progression. So we're starting out with a partial pressure of O2 in the water of 0. We're going to reach equilibrium until these pressures are the same, but pressure doesn't mean the amount is exactly the same, right? We're going to have moving of these gases until we have a pressure of oxygen in the air. We're going to leave it at 100. This container was open to the environment. And a pressure of O2 in the water, also 100. So they reached equilibrium. And that equilibrium means that for the about 5.2 millimoles per liter of oxygen you would have had in the air, I don't expect you to know that number, but that's how much you would have at this partial pressure in air under typical conditions. You'd only have a little bit of oxygen going into the water, that 0.15 millimoles from before. Comparing this to what happens with carbon dioxide. So these green ones are now our carbon dioxide. We start with the same setup. All right. We have a setup, these green guys, they're carbon dioxide. We started with a partial pressure of 100 in the air, partial pressure in the water of 0, come to equilibrium. This is dependent upon the solubility of that gas, how easy it is for this gas to get into the water. So you can see, I think they had drawn 1 little dot of oxygen moving into the water. Now we have 2 little dots of carbon dioxide in the water. Our partial pressures have come to equilibrium. So we are both at 100 millimeters of mercury. And we can see that the amount is larger than it was for the oxygen. So here we have that 3 millimoles that moved into the water versus that 0.15 millimoles when we were looking at oxygen. Even though in the air, when we were looking at those partial pressures, a partial pressure would have been the same for both because they were at the same partial pressure in the air. We didn't have to worry about solubility in air. Okay. So carbon dioxide, much more soluble in water, much more soluble in blood. So we're going to see that those low partial pressures, relatively low partial pressures for carbon dioxide in the air don't necessarily correspond to low amounts of carbon dioxide as we move in and out of the blood. The other thing, I'm just going to tell you from here, we are not going to be talking about these gases in millimoles at any point past just this example of what's happening with the solubility, right? So we're not going to be thinking about that. Instead, we are going to be referring to the partial pressures of the gases, both in our blood and in our air. So you want to know that they come to equilibrium with each other when they're sitting next to each other. They are roughly giving you a kind of proxy for the amounts, but a number for partial pressure for carbon dioxide would mean more carbon dioxide. A number for oxygen for partial pressure would be lower when we're in the blood. Yep. But from here on out, we're really going to be referring to their partial pressures specifically. So let's take a peek through and think about that alveolar air. So specifically, I recommend you look at the oxygen cascade figure that's going to come up in these slides. I want you to find for me what the actual partial pressures for oxygen and carbon dioxide are in typical alveolar air. I'm going to keep us moving, so let's take a look. I'll walk through. Okay, so we got two guesses. All right, so for this first one, the wrong option, that would have been our partial pressure for oxygen. Or, oh, now we're to the right one. Okay, so let's look. Okay, so this is what we had for our partial pressure of oxygen in the atmosphere, right? But as we move to the alveoli, we know we dropped it down as we humidified it, added carbon dioxide. Because we mixed it with dead air, that calculation we did comparing minute ventilation and alveolar ventilation, we would have even another shift. Conveniently for our memories, perhaps, dropping the partial pressure of oxygen in our alveoli down to 100, right? So oxygen 100, great. That's going to be like kind of the baseline number you want to remember for partial pressure of oxygen. It happens to be the case that carbon dioxide has a partial pressure of 40 in the alveolar air. And so we're going to be thinking about what that means for your gas exchange in the lungs and what that means for the amount of gas that you have moving through different parts of your circulatory system, and especially what's going on as we pass respiring tissue, aka cells that are doing stuff. Okay. So we've got gas exchange happening in the lungs in the respiratory zone. We've got gas exchange happening at the bottom of all our figures as our blood passes capillaries sitting next to cells that are doing stuff, our respiring tissue. And anywhere along our circulatory system, we'd be able to measure or report our amounts of gases in the blood, which we would be expressing using these partial pressures, partial pressure of oxygen, partial pressure of carbon dioxide. Okay. So what we want to remember about gases and just how things behave, right? Gases, like everything else, are going to move down gradients. So they're going to move from high pressure to low pressure. We know that was true with pulmonary ventilation as we were breathing in and out of the lungs. This is also true when we look at partial pressures and we're looking at comparing a partial pressure of a gas in your alveolus versus in the pulmonary capillaries, or if we're thinking about a partial pressure of gases in the fluid around your respiring tissue versus the partial pressure of that gas in the blood that's passing it. Okay. So gases go down pressure gradients. In gas mixtures, they also go down gradients. They're going to go down their own gradient when we're thinking about these partial pressures and we're thinking about the lungs and the tissue. So when you're thinking about which direction is oxygen going, you're thinking, what is the partial pressure of oxygen in this place versus the other place that you're looking at, right? You don't have to think about all the other partial pressures if you're tracing just one gas. So presence of other gases is going to be irrelevant once we have our partial pressures. Okay. So here we have a picture of our oxygen cascade. Okay. So I'm going to ask you to think about it. So what I'll do is just point out what's going on with the anatomy in this picture. Then I'll ask you a question to do a little detailed reading here, and we'll come back to it. Okay. But what we're looking at is we've got our heart. We know the right side and the left side do different things. Okay. So we know that from the right side of the heart, arteries always go away. All right. So this is a pulmonary artery. All right. So those pulmonary arteries are going to your lungs with the goal of dropping off their carbon dioxide and picking up oxygen. Okay. Our pulmonary veins always come back to the heart. So this was our pulmonary circuit from last semester. Right, so our pulmonary veins come to the left side of the heart, to that atrium. And then that blood leaves through your systemic arteries. So like the aorta and then your arteries. And we are heading towards capillaries that pass by tissue. Right. Then we're going to come back to the heart, ultimately through the right atrium, through our superior, inferior vena cava, in general, systemic veins. Okay. So these are the places we are thinking about our gases moving through the blood. We've got capillaries up here. So those are pulmonary capillaries. And we've got systemic capillaries down here. So what we are going to want to be tracing when we think about the oxygen cascade is how much oxygen do we have in these blood vessels? Where do we see shifts? And on this figure, you can also see the shifts in carbon dioxide. Okay. So I'm going to ask you to take a look at that figure and pay attention to the oxygen specifically. So go ahead and look at those partial pressures of oxygen. And I want you to find, where did the number change? Right? So where did we see a change in that partial pressure of oxygen? The whole big figure is messy, but if you focus on the right parts, it gets pretty easy. Okay, let's take a peek so we can talk through it. Okay, cool. Yeah, so we had changes twice, basically. So looking at this, right, if we're trying to simplify this, we're going to be thinking about lungs. All right, we're going to be thinking about the right side of the heart and the left side of the heart. Okay, we're going to be thinking about tissue. Okay, so we mentioned already our alveolar air starts out with a partial pressure of oxygen of 100 because of the humidifying of that air, because of mixing with our dead air, drops it down from our normal atmospheric conditions, okay? We then come to equilibrium right here with the pulmonary capillaries, right? So both these places, alveoli and pulmonary capillaries, we would measure that partial pressure of oxygen at 100. Okay. That number is not going to change until we actually have gas cross into a new place, into a new cell type, right? So that blood stays at 100 in the pulmonary veins as we go to the left side of the heart, stays at 100 as we come out the aorta, stays at 100 as we approach the tissue, and then it's at that tissue where we have respiration happening. We need oxygen. We're using oxygen. This is where we see our drop, right? So here we see that our cells, because they're using oxygen, have a much lower partial pressure of oxygen, right? Now, when gas exchange happens until we reach equilibrium. The blood is moving slowly enough through the capillaries for that to happen. All right, so now our partial pressure of oxygen drops to reach equilibrium with that gas in the tissue. So it drops down to 40, okay? And it stays at 40 in our systemic veins, coming back to the right side of the heart, stays at 40 as it goes out our pulmonary arteries until it gets to those pulmonary capillaries and does gas exchange again, bringing itself back up to 100. Yep. So if I ask you what the partial pressure of oxygen is at any point on this loop, all you really want to remember, you do need to know the order of blood vessels from the heart and the lungs. But other than that, you just need to know, is the last place we traded our gases in the lungs, or is the last place we traded our gases at the tissue, right? So if you can trace where the blood has been, you know what it needs to be. Carbon dioxide, we could do the same thing, right? So carbon dioxide, I'll erase our specific gas, but we're going to have this happening at the same two places. Nothing is changing about our arrangement of vessels, just the gas we're chasing. We only need to think about that specific gas, right? So up here at the lungs, we've got our partial pressure of carbon dioxide at 40. Okay. Stays at 40 as we move through our whole systemic circuit until we get to tissue. That tissue is making carbon dioxide. So now we can see we picked up some extra carbon dioxide. We came to equilibrium with that tissue. We've been making extra carbon dioxide. All right, so now our pressure is up to 46. Okay. And it stays at 46 as we return to the heart, as we move through the heart, until we get back to those capillaries that are coming past the lungs. Okay. So the numbers you need to remember for oxygen, 100 is our freshly oxygenated blood. We drop down to 40 for oxygen as we pass tissue. Carbon dioxide, that is just a coincidence that carbon dioxide is at 40 in the lungs, right? 46 is after we pick up extra carbon dioxide at tissue, right? So you really only have three numbers, 100, 40, and 46 that you need to remember for our whole oxygen cascade and our exchange of carbon dioxide, so long as you remember the order of blood flow through these places. So all of this is happening fast. We got a small diffusional barrier between alveoli and the blood. Same thing with capillaries. We know that capillaries in the systemic system, like their point is to exchange stuff. Small barrier, large surface area. So these next two figures just show you that that change is rapid. So about a third of the capillary is used for this gas exchange, both for oxygen and for carbon dioxide. So we'll pick up here on Friday to finish a couple things out. I'll get a practice exam up sometime soon because our exam is coming up on Monday next week. And on Wednesday, I don't see you because we got community day.